literally just one more step. You're doing a translation, and then they want you to do a reflection. And as we'll see that over the course, get back into our notes then, this is what we call a composition. A composition is more than one thing happening. So this is a composition of transformations. So we have a translation and then a reflection. All right, as we talked then yesterday, applying that rule for the translation, as Sam here was pointing out, we're going, let me grab stuff here, okay. It says do 3 units left and then 2 units down. So as I, excuse me, look at this, let's take a look here real quick. 1, 3 units to the left should put me at what? That should be a -2 here anyway, shouldn't it? Yeah, it should be a negative there. So as we do that right there, all right, 3 units left, that's the x-axis, so we're subtracting 3, and that should have been a -2 off of that one. And then we go, what, 2 down, -2, 2 down, that's the y, -4. And then we keep doing that for the other 2 coordinates. All right, we start up at 3, 3 to the left is a -3, 0, that makes sense, -4, down 2, -6, that works. And then the other one is the same thing. 3 to the left, 0, that makes sense, down 2, okay, that looks good. Now that answer though is not my final answer. That is just the translation. So now we're going to apply a reflection here. So when we apply that reflection over the, the y-axis, all right, if you don't, we talked about reflections yesterday, but I gave you a picture of those. So if you're not quite sure what a reflection over the y-axis does, make a sketch off to the side, take a point for yourself, and just reflect it to see there is a pattern happening there with the reflection over the y-axis. So let's say there is a point right here located at 2, let me try this again, 2 comma, -1. Let's say we have a point right there, okay? And we want to reflect it over the y-axis. So if we reflect it over the y-axis, we know our y-axis is right here, okay? Follow that point, and then as you follow that point, something happens with those coordinates, okay? When I reflect it over the y-axis, we go from right to left. Where's this point now going to land at? Okay, it's 2 away, and then 2 away puts me at -2, right? -2 comma 1. So we started off here, and then we ended right there. What stayed the same and what changed? The y-coordinate stayed the same, and the x-coordinate is the one that became its opposite, right? So it started off as a +2, we flip it over, it becomes a -2. If I were to do it, starting off over here at, say, -5, 3, okay? If I reflected over -5, 3 over the y-axis, same pattern's going to happen. You're going to change the sign of the, you're going to change the sign of the x-coordinate, but the y-coordinate's going to stay the same. So what we're now going to apply then is a reflection to that right there. Somebody there? Okay, so we're going to apply that reflection out to the coordinates there. Thank you, Silas. So what we end up with then is, actually our final answer here is this right here. Now I'm going to call this a double prime. All right. If we apply another transformation, we throw another prime in there. Got another one, Mark? Okay, we apply then another transformation, we throw another prime in there, and we call that a double prime. And we can throw another one in there, we call it a triple prime. Usually the highest we go is a double prime though. Okay? So with that in mind, my final answer should be coming right here now. All right, reflection of the y-axis, kind of keep in mind what we just did. The y-coordinate stays as is, but the x-coordinate becomes its opposite. So this should be at what? 2, -4. H double prime, okay? Now it's at 0. 0 going to change anything? No. And then the y-coordinate, we stayed at -6. What's changing is that x-coordinate. It's becoming its opposite. That's what I'm focusing on right there on these couple examples. And then S double prime, we're at 0 again. and there we go. So I think what I had there is actually the final answer on that one there, but because of the zeros, it kind of made things look a little odd. So what I did have for there is the final answer. Now, when we put the final answer out there, it just kind of depends on how you do it sometimes. I put double primes out there just now, working through that, and that is fine. I will have answer blanks there. Whatever's on your answer blank, I'm grading. So a lot of times students will then come back around and then just say, this is my final answer, the single prime. It's not wrong by any means, okay? It's just that when you start throwing in double primes, triple primes, where am I actually kind of looking at? It's, I don't want to say ambiguous, but it is kind of up in the air sometimes of what you want to do. Again, one more time, there'll be an answer blanks there. Whatever you put in the answer blank, that's what I'm grading. And if you don't put in the answer blank, I'm grading whatever you got floating around there, right or wrong, okay? All right, so there's that. That's a composition. Compositions is just more than one transformation occurring. It could be two translations, it could be two reflections, you can throw in a rotation as well. All right, but that's what we call as a composition. All right, that was number what, 3? Other ones anybody's got. This is your time to ask about. Is that hand up, Andrew? 4? Sure. Number 4, take a minute, let's read through number 4. All right, in the right triangle, triangle ABC, we get angle B is 90 degrees, AC is 9, BC is 6. And it then says all the vertices are in quadrant 2. So if it's, say, helpful for you, okay, maybe go through and, say, sketch out that picture. Is it necessary? Not always, but it might be helpful here. So it says it's in quadrant 2. We got a triangle. More specifically, it is a right triangle, okay? And as I label this out, B gets the 90. Don't care where A and C are going, but that's what we essentially got going there. There's quadrant 2. It's all in there. Okay, AC is what? A length of 9, so that's my hypotenuse. BC is a length of 6. That's my leg. Okay, so then it says it does a reflection over the x-axis, and then it does a translation 2 units right, 3 units down, to get me my final triangle there. What is the length of AB? I have an answer of 3 root 5. Doesn't matter what I do to that triangle. I could rotate it. I could throw in a rotation here at the same time. All right. I can throw another translation here. Is that triangle staying the same shape and size though? Yeah. Yesterday we said it's an isometry. Isometries for translations, reflections, rotations all preserve the same shape and same size. So what again we can do here is go through and try to capture this, but it's not going to capture it, is it? Let's see if we can do that. Okay. I can take this thing and, like I said, move it all the way around, throw in a rotation to it. Is it changing anything off that? No. Okay, so whatever I want to do with that thing, it's staying the same shape and size. Yeah, it's moving around, but who the heck cares? Okay, throw in a reflection to it as well. Another reflection, I don't care. So all we're doing is good old Pythagorean theorem there. Okay, so with the Pythagorean theorem set up, all right, what do we got here? This is my missing side. We'll call that x. All right, and what is that? X squared plus 6 squared equals 9 squared. Okay. So the idea is on that one, nothing changes it. Who cares? I don't care where it lands. All I care about is what's the length of that. And then what's also going to be true here about the 2 perimeters. As I go through and say calculate that, okay, we get a 3 root 5 there. But from where it started off to where it ended, it's still going to be the same perimeters. The perimeters are going to be the same. They're going to be equal. Because again, you're not changing the shape and size of the triangle there. So, same, it's the same. Area is going to be the same as well. The area doesn't change. The perimeters aren't going to change. It's all going to be the same because it's again an isometry. Okay. All right. Other things anybody's got from last night? That was from number 4 there. Anything else anybody's got? This is your call. Go once, go twice, and looks like we're old. All right, the usual. Make sure your name's on it. Throw in the basket. let's get out your geometry books and let's go ahead and turn it to the next topic. And the next topic is going to be somewhere, I don't know. Page 91, everybody. Page 91. Okay. Just need a pencil, and if you got that patty paper still left out from yesterday, go ahead and grab that patty paper. If you don't have that patty paper, I'll be avoiding that. Okay, grab that patty paper. Yeah, if you don't, I guess. We're going to use that patty paper throughout. Again, this. If you need another one, just raise your hand. Okay. All right. So let's see what you guys kind of remember here. Going back a little bit to algebra. All right, from the last few years, not so much with us right now. We have not talked about this part yet. Okay. Let's see what you guys remember from 7th and 8th grade about functions. All right. Do we remember what the vertical line test is? I know my sophomores we did last year. Okay, Alan.
So taking the line and if it touches two points at one time,
it's not a function, right? So in math we have relations. Well, we start right there. Relation is anything that you pretty much can do it. It could be points. It could be an equation. All right. It could be a graph. It could be a word problem. Whatever. Relation is things happening. When we start breaking that down in 8th grade, 7th and 8th grade, in Algebra 1, we go into a little bit more. We talk about a relation. When is it a function? When is it not? And one of the quick ways when it's a graph like this to classify a relation as a function is what you just said. Take your pencil, all right, put it vertically on your paper. We read graphs left to right. And as we read this graph left to right, what we're trying to see is it passing the vertical line test or not? And in this first instance, as we drag our pencil across, we want our line to hit the graph at one point at a time to be considered a function. So as we drag it across, and she said on this one, it was not a function because as we drag that thing across, I mean, it's hitting more than one point at the same time, vertically. It cannot happen. So on this one, this is where we classify this one as not a function. Okay? All right. Now, number 2. So based off of that and what you guys remember from years past, what do we have on number 2? This is it's a function. Take your pencil again vertically, drag it across. And as we drag that across, as we can see, it is only hitting one point at a time vertically as I keep dragging that across. Nothing vertically is, say, hitting it besides just one at a time. And that's what we then say is considered to be a function. More importantly, or not more importantly, but the next thing is, well, what is that function? What's that graph called? Yeah, we call this a quadratic function. My sophomores, you should be all up on that. Okay. Last year in algebra, we talked about what linear, absolute value, quadratic, and the exponential function. Okay. So this is our quadratic function. This is what we will do a lot more work with at the end, maybe December, but I know in the second semester we'll do a deeper dive into that. Okay. And if you were sitting there going, I don't know what it means to be a function or not, that's some of the algebra we'll do a little bit more on. And go from there. Okay, so let's go ahead and keep moving here. Let's look at this next part. So working through this next topic with you, all right, I'm just going to be straight up honest with you. I don't try to BS you. This topic has got some nice things in it, and then it's got some weird stuff that goes nowhere. And we're going to skip over that crap. So let's skip over that. Let's go to the next page. I think here is, on the next page is where we actually are going to be at. Okay? So it's a little funky. We already did this yesterday, though. Okay? They are doing it not so much in a coordinate grid like we did yesterday, kind of brushing you guys back up on transformations. And as you work on this one, what we have here is a translation happening. Now, yesterday we said translation is a type of isometry. We just did that a few minutes ago with that triangle. I slid it left, right, up and down, whatever the case is, but the orientation stayed the same, right? Just changed positions, kept the size. So on this one here, obviously it's not, there's no coordinate grid there. But what they want us to realize here is a translation is just a rule. It could be on a coordinate grid, they could give you into words, they can give you those rules like we saw yesterday, or we could kind of give it by a rule as what they did here. What they have here is this box, the square is representing some type of function rule happening. And what they're saying here is take this line, this is my input, okay? In algebra, we talked about inputs, outputs. We talked about domain and range. We talked about independent, dependent quantities. You should have in 7th, 8th grade in Algebra 1. What we want to do is take this line and apply this function rule to get whatever the output is looking like. So this is where now our patty paper comes into play. So what I want you to do on that patty paper is, okay, this right here, that line, that is our pre-image. That's our input. So in algebra, we like to think about that as kind of our input. In geometry, we call that our pre-image. And what I want you to do is, just on your patty paper, put it on there and trace over that line, that vertical line there. And then also put that point on there. As you can see, there's a point on that line. We're going to use that point to then follow the function rule, okay? So using that patty paper can be used for any of the types of transformations. Now we're going to use it for a translation here. Now what I want you to do is take that point and follow it along that path to where that point here lands on this output over here. And as you do that, what is happening to that vertical line? Tell me the direction it's going. It's going what and what? It's going right and down. That's what I'm looking for, right? So this is going right and down, okay? And then once you draw that, okay, you take that patty paper, you slide it right and down, just like we did yesterday with the rotations, okay? Go ahead and draw that line underneath there at the end of that output. So I'm looking for a line, you know, looking kind of like that then, right? So as we slide that, that's a slide. We slid to the right, we slid down, that gives us our same shape. This is again what we call an isometry. So what I'm looking for from you guys is what you have on your patty paper, all right, looking something sort of like that, right? Okay. Now as we did that, what do we notice here about those two vertical lines? Our pre-image and now our image. What's true about these two lines then? Parallel. Thank you. What we end up with then is parallel lines. The pre-image and image are parallel, just like Eric said there, okay? And that's going to be happening here. As we slide these things left, right, up, down, whatever the case is, okay? We're not flipping anything, we're not rotating everything. So as we move these around, you're creating a bunch of parallels. We didn't talk about that yesterday, who really cares, all right? But as you do a translation here, these are all going to be parallel no matter which way you move it. If we moved it to the left and up, do we still get parallel lines then? Yeah. If we just move it to the left, yeah. If we move it down, that's a little bit of a funky one, right? If we move it down, is it still parallel to this original one? No, it's not parallel, it's on the same one, right? That's about the only time up and down things get a little funky with parallel or not. But if we do everything else there, throwing in some left-right movements, we still are going to be parallel, okay? So with our translation there, what we want to keep emphasizing to you, as I'm going to keep telling you, is it preserves size. And what we call this translation, not just an isometry, we call this a rigid motion. A rigid motion preserves size. Rigid motion, left and right, up and down. Okay, as we'll do the flips later on and the rotates later on, those are what we call rigid motions. All right, let's keep going here because there's not a lot to talk about. So now what I want you to do is on the next one, take that same kind of vertical line, but this time we have three 3 points on there. What I'd like you to do with those 3 points is plot those on there as well, and make sure those 3 points follow along that function rule, that translation rule. Again, what you should then see is another set of parallel lines up here, right? As you drag that across, use that patty paper, drag that across. So we can use that patty paper for everything, and what we have again is what we say is rigid motions happening. And rigid motions preserves that same shape, same size. When it doesn't happen like that, we get into something else, which is a non-isometry, we'll talk about this next semester. Okay? So as you drag that across, does it give you the same vertical line? I guess is what I'm trying to say. Yeah, it does. Okay, slide it down, so we're going what? To the right and down again. And what you end up with then is a line, something like that, right? Okay. So, nothing really changes with those there. What do we notice about these 3 lines right here in the middle then? In order for that to happen, they have to be parallel to one another. So, these 3 lines must be parallel to preserve congruence. And if those things are not parallel, we end up with something else there. We'll talk about that something else later on. Okay. All right. Give you a second there. Whoops, sorry. Go back one. Go back up. Things got a little funky there. All right, bless you. Don't care about that. We talked about patty paper. Don't care about that now. So let's go ahead and flip it. So this next part then is talking about, whoops, went too far, is talking a little about, they throw in the last part here, rotations, okay? So as we talk about rotations, starting to figure out what is the angle of rotation. What we did yesterday was rotate about what? We rotate most of those about the origin, right? In just a minute, we'll finish this up and go back and do a rotation around a non-origin point. But that's on the coordinate grid. What we have going here then is obviously nothing on the coordinate grid. So what we want to go ahead and try to figure out is, what is the degree of rotation? What's the degree of rotation that's the minimum to say turn it onto itself? We can rotate this whatever we want to do, but it doesn't then rotate onto itself. As we see here, what we have here is like a plus sign. On what they did is a rotation of 45 degrees. Okay, so they rotate at 45 degrees, and what we want to then start talking about here is, we didn't talk about this yesterday. We talked about clockwise and counterclockwise, but in math, our rotations can also take on either positive or negative, and depending what that positive or negative is, tells me it was either counterclockwise or clockwise. So as we look at these 2 things here, this one went positive 45 degrees. That is our default. So that's our default, and when it's a positive rotation like that, we say that is counterclockwise rotation. So you will not always see counterclockwise label, or the shortcut, the shorthand, I will use CCW. If those are not stated and they just tell you it's a 45-degree rotation, in your head you default to counter. And then on the other side of things, if it is a negative degree rotation, that is to say it is a clockwise rotation. So if I don't tell you to go clockwise, but I say do a negative 60 or negative 100-degree rotation, that is understood to then be a clockwise rotation. Just one of those things in math, by the way. As you guys go into Algebra 2, you are, again, sophomores, so next year might be signing up for physics. You'll do a lot of work with that in physics. All right, so just file away in math and your science brains there, okay? Now, we can rotate it wherever, but what we then will talk about as we work throughout this topic is also trying to make sure it lands on itself, okay? So what do I mean by lands on itself? All right, let's take a look at this triangle I have right here. All right, what I want you to do on that triangle is, I'm gonna bring it up as well, just a little bit larger here, is I want you to go ahead and put a point right there in the middle of it. Okay, put a point right there in the middle. And then after that, I want you to divide that up equally. So, middle of that, yeah, your triangle right there. Okay, divide it equally. All right, how many equal spots, equal smaller triangles can I create out of this? 2. I can create 3 other equal triangles, right? So as you do that, right there in the middle, where are those 3 equal triangles coming from? From the vertex to the center, right? So in every polygon we're going to do here, all right, we can go about cutting these all up into equal triangles. Now, when I do that here with you, okay, next thing I want to figure out then is, whoops, not that. Grab that for me. Oops, if I grab it. All right, is then to figure out the degree of rotation here that will land on itself. It starts right there at that center that you found. How many degrees in the center? When you walk this thing around, okay, how many degrees are around that circle? Let's try this again. How many degrees are right here? Somebody's saying it. 360 degrees, right? And that 360 degrees is getting cut up equally 3 ways, right? So how much is each of those 3 angles then? 120 degrees, right? So with that being 120 degrees, if we were to then to rotate this thing, okay, you should be getting pretty much that same orientation. It should kind of land back on itself. So what we say on this particular dude, that this has a degree of rotation of 120 degrees, okay? And what we then follow up by saying here is, it has rotational, and you've heard of this word before, rotational symmetry. Okay, in algebra classes, I know we've talked about the word symmetry, the vertical axis symmetry, and in geometry, we're going to be doing some of that as well here with things. We have our rotational symmetry. And whatever that smallest turn is, that smallest degree is, that's the degree of rotation. So for this particular triangle that we did, this has what we say is 120 degree rotational symmetry. What if it's not a triangle? What if we got ourselves a hexagon? Come on, hexagon. All right. So what if we got ourselves a hexagon? How many equal triangles are going to have in there? If I put that center in there, how many equal triangles am I going to have there? 6 triangles, right? So I cut it up equally. And I ask you that same follow-up question. Okay? What is one turn of that hexagon? What's one turn of that hexagon so it lands on itself? What is that internal angle right there going to be? 360 divided by 6 equal pieces, right? So each of these, yep, is 60. So in a hexagon, we say its rotational symmetry is 60 degrees. All right, how about this next one here? Let's go with a octagon. How many equal triangles in an octagon? 8. Now what is that degree rotation there? You don't have your calculator out, you might have your phone out. What's 360 divided by 8 give you?
45.
Thank you. Keep forgetting to click that over. Yeah, that's a 45 degree rotation. So we say that this octagon has 45 degree rotational symmetry, and so on and so on and so on. So we're going to be talking about, I think in the next topic, this transformation stuff leads into that, is figuring out, we call right there is what we say is the central angle. That central angle right there is what we're going to be talking about. It's nothing crazy, but it leads right from our symmetry stuff into some work right there. Okay. All right, that's where we're going to pause that. So let's go ahead and get out and finish this thing off. Get out those notes from yesterday. We did rotations at the end when we ran out of time. The one that we did not get to is the rotation on a point, not the origin. So get that out real quick. All right. Again, keep that patty paper out. All right. So rotations that we reviewed on yesterday. All right. Doing a rotation about a point that is not the origin. So as we did yesterday on our patty paper, we're gonna do the same thing. The only difference is when I put that patty paper on there, I'm not gonna put that mini XY axis at the origin. Where am I gonna put that mini XY axis at? Let's finish this off. Where am I gonna put that mini XY axis off on number 20 here? I'm gonna put it on at -1, -1. So if you keep going back to the origin, that they tell you to rotate about a different point, you're not going to land up where you should. Probably what's going to happen is you're going to land off the paper maybe sometimes. So on this one, take your patty paper, again, throw it on there, and I'm going to, again, freak my board out here. Yesterday. As I put that on there, I'm putting that mini XY axis to keep track of my rotation at -1, -1. Yep, there it goes. All right, so on my patty paper, I'm at the point -1, -1. I transfer over my, my pre-image. And then I'm gonna rotate it whatever they tell me to do. But you gotta have that mini XY axis this time at the -1, -1. That is my point of rotation. If you put it at 0, 0, it's not gonna come out to be at nice locations. So on my patty paper, I get the same thing, just like we did yesterday, but that mini XY axis is at -1, -1. And now let's rotate it. 180 degrees, which way? Counterclockwise. Follow the clock if you need to go counter to that. And as I do that then, okay, counterclockwise, 1 over that, and how many turns do I need to do? 2 turns. And as I do those 2 turns, it's hard for me to kind of do it up here. But what you should be ending up with is that triangle. It looks like up here, majority of it is in quadrant 1, it looks like. And then some of it's going to end up in quadrant 2 and a little bit, I think, in quadrant 3. If I remember, if I can see it correctly. All right. I am just going to freehand that because it's, like I said, impossible to kind of do right here. There it goes. So you're ending up with kind of something like this, roughly like that. I know it's not at all the scale or the right picture, but she ended up something roughly like that. Okay. Maybe too much in the bottom quadrant there. Okay. Maybe a little bit more up top in quadrant 1. Something like that. Okay. On the other one, last one there, it says rotate about 0.3. So when I go back to my patty paper, I'm again putting my mini XY axis not at the origin, but at that point of rotation this time, which is at 0.3. And then I trace over my pre-image onto the patty paper. And then I turn my paper, whatever direction it says, but make sure you're turning it on that point 0.3. That's where I put that mini XY axis. That mini XY axis helps you keep track of those nice 90-degree turns. Okay. So on 21 then, counterclockwise, 90 degrees. That's 1 turn in my paper. But again, you better make sure you're at 0.3. If you're at the origin, I know it's gonna go off the paper, I think. But 0.3, it should not. Okay, I don't think so. Hopefully not. So as I freak out my board one more time here. Okay, there it goes. Let's see. Get out of the way. That does not work very well. 1, 2, 3. And boom, boom, boom. Counterclockwise. Okay, counterclockwise. That's the wrong direction. So counterclockwise is that. 90 helps if I turn it the right way. 1 turn right here. So looks like it's kind of over here then. Somebody else get that same? Yeah. Okay. Kind of looks like over here in quadrants. What is that? 1 and 4, I believe. All right. So rotations are pretty straightforward with 90 degrees. Not as much when they're not 90-degree rotations. We'll talk about that next week sometime. Maybe it's even the following week, how our schedule pans out. Okay? But as we finish up here today, if you again have any questions about doing your rotations here, this is the time to ask us out. Translations, reflections are pretty straightforward. Rotations aren't bad once you figure out how to use that patty paper. But again, this is the time to ask about it. All right? Tomorrow we'll come in. We'll do a bit more work here with our transformations. And then Friday, we'll just kind of continue on. Next week, things get a little funky. Friday, next week, things get a little funky because of the Tuesday and Thursday, Tuesday and Friday. Yep, because Tuesday and Friday we're off. So we'll have to just deal with that. Tentatively, what we plan on doing here is, next Thursday will be our first quiz over these topics next Thursday. Okay? Just that choppy week. There you go. And here comes, one more time, if you need more patty paper, they're inside my desk, it's back there.